Okay, well, let me pause this for a minute. Are you actually... Right, let me stop this very quickly. Shushed. Oh, that was just intro anyway. So I'm trying to make sure I'm actually sharing what I think I'm sharing. Okay. That didn't work the way I did. Are you seeing a big screen saying vector field on it? You are, okay. So I can't do much about the sound, but I'll try and just explain what's going on here then. So there's a vector field. That's a vector field changing through time. Here's an example of an electric field. That's what it would look like in 3D, but it would hurt your brain. We're saying, look, a vector field can use to represent different situations, although they don't necessarily seem to be connected. Right. So we use fluid flow as a very generic way of describing many vector fields. Right. Now, I'm going to pause here. If you look at this vector field, for want of a better description, can you see that there's like hotspots where something interesting is happening? And there are two kinds of hotspots. In this place over here, do you see that the preponderance of the vectors are all homing in on that place? And this one is also. Do you see over here, there's a kind of, everything is trying to get away from that place. So when you calculate the divergence, it will be a positive number or it will be a negative number at any given point, right? X, Y, Z, or X, Y if it's 2D. And if that number is everything's coming in, that you get one value. If it's everything going out, you get a different value. So it's like a white hole spewing out matter. And the others are like black holes sucking in matter.
I just wanted to
So the places where the vectors are all leaving, trying to get out of there, that will be a positive divergence. And if you're going the other way, it's negative. So if I can jump ahead, this is what Curl does. Let me pause this. If you imagine some object, or not some object, a vector field at some of these key places, at any given point, when you take account of everything around it, there is very often a kind of rotational movement going on, like a current flow. And if it goes in an anti-counterclockwise direction, the curl at that point will be a positive. And if it goes the other way, clockwise, it's considered to have a negative curl. So if you can imagine that picture as being some kind of wind system. Do you know those little windmill sticks that you have, that plastic little things that whirl around, right? Can you imagine taking one of them and sticking it in certain places? Wouldn't the thing turn clockwise or anti-clockwise depending on the basic rotation process that's going on? And what the curl measures is the rotational, what's happening at that point in terms of rotational movement. And it doesn't necessarily have to be everybody is going in the same rotation. It just needs to be that there's more pushing it one way than the other. So can you imagine in this situation, there's a lot of flow going this way and less flow going that way. So if this was a wheel, like a paddle wheel, and there was some kind of current going on here, you see this top one would be forcing it going down. This bottom one would be trying to force it going up. But if this is stronger than this, won't the net effect be to rotate this way, to rotate in a clockwise direction? So we're going to be learning total theoretical stuff here. We're going to basically find out how to calculate a curl and a div. But I thought it might be worthwhile just to show you what on earth those things are, right? Because you might say, what am I finding here, right? What does it look like? So I'm going to stop sharing that fella, and I'm now going to hopefully try this fella. Come on. See, I got my new gizmo. So, what a preparation today. That first bit was just to get you a theory. Next preparation. Can you remember in Calc 3 getting the determinant of a 3 by 3 matrix? The cross product. You remember doing those, guys? Right. So I want you to think of that process. So I'm going to do it with numbers. Suppose I have a vector u and I have a vector v, and I'm going to call this guy 1, 2, 3. And I'm going to call this guy 5, 1, minus 1. If I asked you to find the cross product, we would set up a 3 by 3 matrix, and we would calculate essentially what is its determinant. The top row is I, J, and K. U comes next, and V comes last. So I'm just showing you how to calculate this thing with numbers, because we are going to be using that to calculate this process, to calculate what's called the curl. And it's quite messy process to do. So you're getting the shortcut version. Remember, it was to do with I, J, and K. Can you also remember, because a lot of people forget, isn't it negative whatever the J value is? And then you essentially do your calculation like this. You want to know the coefficient of I, right? How many of vector I you get. You remember that you would cover up column I. And then what would you do with this little 2 by 2 matrix of numbers that you've got left? You remember what? Say again?
Take the determinant.
Right, so it would be major, -2, take away -3, so -2, take away 3, I get -5. Now you want the J guy. Cover up the J column, right? Major diagonal -1, take away minor 15, I make that -16. You want the K component. Is this coming back to you? Right, I, J, K, covering up the column. Now, major diagonal 1, take away 10, 1 take away 10 is -9. And I like these answers as -5 plus 16, negative 9. Have you noticed that the middle term is positive 16 because you subtract the J value? And that's the mechanics of cross products, right? Determinant of a 3 by 3 matrix is a 3 by 3. Now, in the context of this question, what you've just found is a matrix that's a vector that's perpendicular to the other two. So far, so good? Right, so that's just a skill building, just to remember how to do it. Another skill. Delta on its own, not delta F, but just delta on its own. It's called an operator. It means it's a thing that does something, right? It's an operator. And the delta operator is this fella. Now you notice that there's nothing next to the delta, right? It's d blank by dx, right? So that's an operator. It says you're going to find the partial derivative of something with respect to x. We just don't know what the something is yet. And that's the partial derivative with respect to y of something, and that's the partial derivative of z with respect to something. Okay. Now, our generic vector fields, right? It's going to be called P, Q, and R. It might be x squared y, x plus z, z cubed minus x, right? It's going to have looks like that, right? So P is just what goes first. Q is going to represent the middle term, right? And Z is going to, and R is going to represent the Z term, right? The third term. So our first fella, what is the thing they call the curl of F? How are you going to represent that rotation? In a 2D world, the rotation is basically just going to be a scalar, but in 3D, it's going to be a vector. So let's see what we get. It's the cross product of delta with F. Cross product of the operator with the vector field F. Now, I know how to do cross products. It's an I, it's a J, it's a K. Delta comes first, so the operator goes here. And F goes second, and it's made up of 3 components. So far, so good. So when we find this fella, right, the cross product of the operator delta with F, we will end up with a vector, right, a 3-dimensional vector that is representing the curl. It's essentially representing the curvature or the curve, how do you phrase this? The tendency of the thing to rotate in 3Ds. And it's basically pointing in the direction of that rotation in 3D world, at least. So in this case, it's going to go I, J, and K. This guy's just going to stay put for a minute. This guy is going to stay put. This guy is going to stay as put. And in the question I've got here, we're going to go x squared y, we're going to go x plus z, and we're going to go z cubed, take away x.
Does the perpendicularity have anything to do with this, or is this a completely separate concept?
Say that again.
Well, with the original vectors, you're finding a perpendicular vector. Does the perpendicularity have something to do with this, or is this a completely separate concept?
My brain is scanning through. There is, if you look at the theory of where these things come from, the proof of why this is what it is comes by using a normal vector. And you know, when you do the normal vector, it's perpendicular to the direction vector of its derivative. So I've got a feeling, but I don't quote me on this because I'm not an engineer, but I've got a feeling that your answer is yes, it is connected to that, but I don't know enough details. It's not my
Okay, but it's
my thing.
It's not important right now, though, right?
No, it makes no. If you knew that or you didn't know, it wouldn't make any difference to getting the answer.
Okay.
Right. Now, so in this question or this guy that I've got here, I'm going to have to. Oh, I can just move my piece of paper. If I cover up the I guy, right? I'll use this pen. We are going to get the curl of F. It's going to be so many I's, take away so many J's, right? Plus so many K's. We're all comfortable about that bit, right? Now, when you cover up this guy, do you notice that the little guy you've got left is the top row never marks, right? We never used it in the other example. But basically, the major diagonal take away the minor diagonal isn't a multiplication anymore. It's actually a process. Can you see that when you put this and this together, aren't you finding the partial derivative with, I'll write it down, that's the best way. Aren't you finding the partial derivative with respect to y of z cubed take away x? Subtract the partial derivative of x add z with respect to z. So let's see what that looks like. What's the partial derivative of z cubed minus x with respect to y? So many
Cubed y minus xy.
Partial derivative of z cubed minus x with respect to y.
0.
0, yeah. What's the partial derivative of x plus z with respect to z?
1.
Right, so take away 1. So that's the I component. It happens to be a number, but that's pretty rare. Let's look at the next one. If I wanted to get this fella, the middle one, do you see it's going to be this, take away that? So this is definitely not enough space to do what I need to do, but it's going to be the partial derivative with respect to x of z cubed take away x, subtract the partial derivative with respect to z of x squared y. And if you do the first one, z cubed minus x with respect to x, you get -1. And if you do the second one, you get 0. Oh dear. Right, I better not get a number for the third one. I just seem to be getting lucky or unlucky. Yay, good. Third one coming up. This major diagonal is the partial derivative of x plus z with respect to x, which is 1. Take away that guy, which is x squared. Yay, good. So our curl is -1. That's negative. 2 more negatives make it a 1. And this fella here gives me that. That's essentially what you're going to end up spending a lot of your time doing, calculating the curl. Now, do you notice that in this particular case, the curl is -1, 1, and 1 minus x squared? What that is telling me is that, say for this particular vector field, if you imagine, you know, doing it in 3D and having lots of little arrows, do you know it doesn't care what these two numbers are? In fact, these two numbers are fixed. Doesn't it only care about what the x coordinate is? So in this vector field, the z direction is affected by the x coordinate of the point. So if you can imagine the curl being a little vector representing how this object is trying to rotate, what you're kind of getting is that it rotates in the direction -1, 1, comma, whatever 1 minus x squared happens to be. Visualizing that is making my head hurt. So all we need to do is say, okay, that's how you can do it. Now, if I go back to this line here, remember this guy here? Since I've got this set up here as the general version of every curl in the universe, couldn't I do what I just did as a general formula? In which case, if you can remember the general formula, at least write it down. Can't you use that to get the answer instead of kind of fighting your way through all these individual one at a time situations? Now, let's see how that works then. If you cover up this guy, your answer is going to be major diagonal take away minor. The major diagonal is the derivative of r with respect to y. Take away the derivative of q with respect to z. Come on. Great. Major, take away minor. So far, so good. Now, I'm about to do the j component. Be careful here. Don't you have to subtract your answer when you do the j component? Right? So whatever you get, you stick a negative in front of it. So if you do this guy, take away that guy, and then you subtract it, don't you basically get this guy, take away that guy? You kind of reverse the order. So instead of going major, take away minor, I'm going to go minor, take away major. And the minor one is this guy with respect to z, take away this guy with respect to x. And now to the third one. This guy with respect to x, take away this guy with respect to y. That represents the general formula for calculating every curl in the universe, every three-dimensional curl in the universe. You see, it's basically made up of subtractions of various pairs of partial derivatives. Now, if you've got a great memory, you can write that down and just memorize it, or I guess you could write it down and just have it beside you when you do the questions. I would suggest that this method here is less onerous than having to do it individually, as you can see me trying to do it up here, right? But you could do every one the way I did these ones, right? You could do it. You could do this and go through the process, or you could do that. I bet you if you started with this equation here, this vector field here, and you used this formula, you'd end up with the same answers. Right, so you know it works. So that's the process. And most of your questions are simply just going to be that. Here is a vector field. Calculate the curl of f or calculate the div of f. Very good. Before I leave curl for a little while and start talking about the divs, what does a curl of f, if it's a zero vector, tell you? So you've got a big vector field, and no matter where you look, the curl of f is 0.
It's a uniform vector field.
Yeah, it's just everybody going left or everybody going up or everybody going down. It would be a very simple flow, wouldn't it? So, and there wouldn't even be any changes. Wouldn't all the vectors be the same length and pointing in the same direction? So you wouldn't be, it'd be a very boring vector field, right? It wouldn't have anything. You could even have it going at an angle of 45 degrees, couldn't you? All the vectors going at 45 degrees to each other, and all at the same length because they're all going at the same speed. Okay, that's how to do the curl. Sorry, the curl. How you do the div. Here we go. So for any vector field f, called PQR again, the div, short for divergence, is defined as the dot product of the operator delta with your vector field f. So can you imagine taking your operator and you're doing this? Now, don't think of these things as being multiplied. Think of this as being the operator on this. So can you see how you get this guy plus this guy plus this guy. What does that tell me? It tells me that the div is a scalar. Wouldn't that be a single number, right, for any given value? It's not a vector, right? It's not something, comma, something, comma, something, right? It's just a single expression made up of x, y's, and z's, all jumbled up. If you choose a point at random, and that point is positive, right? So the div is positive. It means at that point in space, more stuff is leaving than is coming in, right? If it is negative, more stuff is coming in than is going out. Right? Now, the div of f is much easier to deal with. It's a very simple formula. It's basically just adding, as you can see, and three partial derivatives together. And they're kind of natural. Doesn't P go with X, Q go with Y, and R go with Z, right? X, Y, Z, first, second, third. They even have a natural direction to it. So I'm just going to pick a random vector field. Oops, start again. Excuse me. So suppose that's your vector field F, and you're being asked to find its divergence. Okay, well, according to our formula, it's the first guy with respect to X, plus the second guy with respect to Y, plus the third guy's partial derivative with respect to Z. Right. You do the first term with respect to X, you get 2xy. You do the second one with respect to Y, and you get e to the x, z. And you do the third one with respect to Z, and you get e to the z, x cubed. Are you all comfortable with that calculation? I don't think you're going to have problems with div, agreed? I mean, as long as you can do partial derivatives 3 times and add them, you're good, right? First guy x, second guy y, third guy z. Well, let's put in some stories. I would like to know what the div is like at the origin. So can you imagine these are 3D vectors pointing all sorts of places. And I'd like to know what's happening at the origin. So is there more stuff leaving? Positive answer. Is more stuff coming in? Negative answer. Is it perfectly balanced, right? The same amount of stuff's coming in as going out. Well, let's see what happens. 2 times nothing plus e to the nothing times nothing, e to the nothing times nothing. And the answer is 0. So it's perfectly balanced, isn't it? The same amount of stuff is coming in as going out. And imagine a point in space where there's forces coming in from the left and then forces leaving on the right, and they're perfectly equal to each other, right? They're perfectly balanced. That would work. How about this guy? I'm trying to do 1, 1, 0, 0. So let's look at the position 1, 0, 0, see what's going on. Well, at that particular point, it's going to be 2xy, 2 times 1 times nothing, plus e to the 1, darn it. Oh, this is okay. E to the 1 times nothing, plus e to the nothing times 1 cubed, good. So nothing add, nothing add, that's 1, add 1, it's positive 1. So can you see at the point 1, 0, 0, there is a net leaving that point, right? So if you looked at all the vectors close to the point in 3D space 1, 0, 0, right? If you imagine a little bubble of interest around that, there would be more stuff leaving that vector, like, you know, imagine like a little explosion and things leaving. There'd be a little bit more leaving than coming in. Now, I believe in fluid dynamics, when you study fluid systems, that it's not that uncommon to have, I think, don't quote me on this because I could be wrong, aren't there things called sinks where things disappear? They're not really disappearing, they're just going somewhere else. But as far as you're concerned, they're leaving the building, right? So I think when you talk about things like fluid flow, you'll be looking at where is something positive divergence, where is something negative, and what that gives you is it kind of gives you an overall picture of what's going on. Right? Are there any questions about the second idea, how to calculate a div? Are we good? So most of your questions are simply going to be, here is a vector function f, find its curl or find its div, right? That's pretty much, so it's going to be quite mechanical, right? Hopefully mechanical. Okay, let's do another curl. I want to just mix and match them up so we can. Here is my vector f. It's going to be sine x, cosine y, e to the z. Just try to keep my life easy. And I'm going to find the curl and the div of this function because they're different things. So if I'm going to get the curl, which is basically that guy, if I decide just to make my life easy, well, I think it's easy anyway, I'm going to use that formula here, right? This one here. So it's this guy with respect to y, take away this guy with respect to z, this guy with respect to z, take away this guy with respect to x, and this guy with respect to x, take away this guy with respect to y. And this is P, this is Q, and this is I. I know how careless I am, so I can tell you that there is a lot of danger in not being careful here. Can you see it'd be dead easy to pick a P when it should be a Q, or differentiate with Y when you should be partial differentiating with Z, you know, those kind of things. So I'm going to try and be slow because that's the only way I can be safe. If you differentiate this guy with respect to Y, you get 0. If you differentiate this guy with respect to Z, you also get 0. If you differentiate this guy with respect to Z, you get 0. If you differentiate this guy with respect to Z, you get 0. I guess I've been too easy on myself. Differentiate this guy, you get 0. And differentiate, oh, come on. I apologize. It is the correct answer, but it's not very interesting because at this point here, there is no curl, right? Oh, there is a curl, it's 0. Okay. Forget my curl and div on that question. X plus Y plus Z. X squared plus Y squared plus Z squared. And X, Y, Z. Why do you think I chose that one?
They all have a term that can be differentiated.
Right, so I'm guaranteeing not to get 0, 0, 0. Agreed? Unless I'm really, really unlucky. Although there is an awful lot of symmetry in this, so who knows, I could be really, really unlucky. And so it's going to be this guy. Middle term's going to be this fella. And the last one going to be this guy. Okay, he's P, he's Q, he's R. Right, differentiate R with respect to Y, you get XZ. Take away Q with respect to Z. Ah, good. P, which is this fella with respect to Z. Take away R, which is this fella with respect to X. Q with respect to X is this guy. P with respect to Y is that guy there. A much nicer answer. At least it's got stuff to it, right? Are we curl with it? Are we okay with the curl? Ugly formula, apply, right? So it's very process driven. Let's find the div of F. So it's the first one with respect to X, add the second one with respect to Y, add the third one with respect to Z. Well, if you take this and differentiate it with X, you get 1. If you take the middle one and you do it with Y, and if you take the last one and you do it with Z, the div is just so much easier to do, isn't it? I mean, it's almost got a flow to it that makes it kind of nice to keep it on track. Is there any questions about curls and divs now? Right. So if you're comfortable with doing the formula and plugging things in, you should be pretty safe. But just be careful, right? Just be careful. Are we good? Any questions? Because I want to just, for the few minutes that we've got left, I want to go in and kind of, if I can, show you what some of the questions from the book looks like. Because sometimes they phrase things in a little different way, and you might say, I wonder what they're asking me to find.
Looking at the homework, it looks like you extended Green's theorem to the 7th, or is there another section of that?
No, there's not another section. It might have been an oversight on my part. I'm not going to cancel it now.
Okay.
Hopefully you should have done it anyway. But, yeah, I didn't know I'd done that. Okay, so Curl and Div. You might not see it yet, but you will see it in a few moments. I have to do this, set it up first, and right. I think I'm ready to show you. Let's share the screen. And sounds like my dog wants to come in and join the party. Right, here we go. This guy here shows you the answers, but hopefully I won't distract you too much. I could take them out if it does. Actually, maybe I should. It's distracting me. I could keep that and just take the solutions out. That's a kind of compromise. How about that? Go away. Good. Are you looking up to the same screen I am? Are you looking at the web assigned homework for this section?
Yes.
Okay, so we can talk about this. Let's look at the standard question. Can you see there's a vector field? Find the curl, find the div. Happens to have 0 curvature, right? And an expression for div. Can you imagine that's just plug and chug with the formula that we've talked about today? Read. Think question 2, question 3. Right. Question 4's got a picture. Right. The vector field F is shown in the XY plane and looks the same in on all horizontal planes. In other words, F is independent of Z. So I guess what they're saying is, can you imagine this being a column going upwards? And they describe the div of it, and then they ask you, in which direction does curl of F point? And it doesn't point in any, because this would be 0, 0, 0. It'd be a flat plane. And there's another one like that. There's another one that goes on. Oh, I didn't realize it went on with that. Do you know this bunch of questions here that's talking about describe each expression, and it says, what's the curl of f? Now, you've got to be careful here. Capital F is a vector field. Little f is the potential function. Remember that little f that you got? It's a scalar function. In other words, you put in an x, y, z, but you only get a single number out as an answer. And it's the same kind of questions, like some things you can find the answer to and other times you can't. So hopefully I'll let you fight your way through that. Back to the normal, right? Well, almost. Find a function f such that it's equal to that. Can you remember that question? Because that question comes from somewhere else. Aren't you essentially being asked to find the, well, you tell me. What does delta tell you to do to something?
Gradient.
Right. So if you find delta f, isn't delta f the gradient function? Now, they haven't phrased it that way, but that's what it is. And can you imagine dx, dy, dz as an operator operating on something? Right? Do you see that you get df by dx, comma, df by dy, comma, df by dz? Don't you get like the gradient function? So basically, to get the answer to that, you would, well, you'd go and you'd differentiate with x, differentiate with y, differentiate with z. And some stuff here about conservative fields, which I'm not that interested in. I don't know what question 11 is doing there because it shouldn't have been. So we'll basically be finishing at 10 here. I'm going to double check on that, but I'm 90% sure that I had no intention of doing those last two. No, I don't. Okay, so you're going to be finishing on, actually it won't be 10, will it? Let's check that. It'll be 9. So are we cool as far as curls and divs go?
I had a quick question.
Sure.
On the question on this homework assignment.
Right. Find it.
How could
This one. Is it?
Yeah.
Yeah, this one. Right.
How could you tell that it was negative? Like, it doesn't give you a point. I'm just confused. Like,
Yeah,
it's
yeah. You see that video that we watched where we zoomed through it quite quickly? If you go and look at that video, what this is trying to show you is that, oh, wait a minute, I'm about to talk myself out.
I think that makes sense.
Right. Jump in.
Because at any point, there's more going in. If you move up along the y-axis, there's more going in than going out because the vectors are getting smaller. So in
You
that
nailed
region,
it. Yes, on my side didn't see that. Big, smaller, 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 right? So let me pick this point here between these two, right? See that point here? Do you notice that the two vectors coming this way, aren't they much bigger? That's heading in towards the point. And what about the two vectors leaving? Do you see that together they're smaller? So wouldn't the net effect there be more going into that point than leaving that point? Yeah. My eyesight just couldn't figure out that they were smaller sizes, but when you say it, they clearly are. So when you're looking at the div, think about choosing a point and is there more bigger vectors coming in towards that point than there is vectors leaving that point? I think the thing about the Z is a distraction because it really doesn't matter because it's just saying every single point above it is the same as what you can see. So that's really all that was there. Now, when it talks about in which direction does the curl F point, and it's talking about none of these, actually, I think a better answer would have been what? 0, I think. there is no curvature going on here. Would you agree? They're all pointing north. There isn't any turning momentum, and they're all stacked upon each other. So there isn't any, the Zs aren't kind of curving you down either, which would generate a curvature, right? It's just a go that way, right? And they're all going that way. Maybe it's slightly different speeds, but they're not changing the direction that they're all going in. So there would be, I think that one would have been better saying a zero curl. A zero curl would happen if it was a uniform field, right? Just something that's got no curvature into it, right? Just directional, everybody pointing the same way, but at different amounts.
Thank you.
I had a quick question about,
Yes.
I think it was number 12.
Is that the one I said I shouldn't have done it?
The thing that I was kind of confused about is, it's talking about doing like calculating like the divergence of like a scalar field.
Right.
So how would you end up going about that? Would you just do the dy or the dx, dy, dz, but just like the whole function and just like add it up, or?
Okay. I'm just going to write down what's here, and then I'll show you what the heck's going on, because I don't think it's easy to see it. Exactly. Actually, 12 is okay. 11 isn't okay. What's 10? 10's okay. Good. I don't know what's wrong with my brain today. Anyway, let's kick out of this and show you that question. That'll probably be the last one we have time for today. So the gist of our question was to find the div of this fella, right? The vector r is a position vector. So anytime you see the vector r and nothing else going on, it means you've got that guy, right? Now, our vector function f is essentially 1 over r to the p times r. So it's that guy. Now, r is the magnitude of this vector. So that makes it x squared plus y squared plus z squared. So what I have is 1 over x squared plus y squared plus z squared to the power of a half raised to the power of p, so essentially that fella, times x times y times z.
I actually selected the wrong problem. The other one is, it's just a really quick question about it. It's like it ends up being a scalar function. I think it ends up being like the scalar of where I wrote it.
Yeah, to save some time here, why don't you kind of put that together as a little question, shoot me an email, and I'll send you out a quick PDF of what the solution would look like, and hopefully that'll answer your question.
All right.
Right. Since I got this one going, and I think I like this question, so I'm going to actually keep this one. Can you imagine that I'm only doing the first one of the three, but can you imagine that would be the guy we'd call P, this one here, right? So if you're going to get the div of f, aren't you going to do the partial derivative of this guy with respect to x? Now that's a very yucky, horrible partial derivative, but if you do a quotient rule and you fight your way through it, you should be able to make that relatively nice. Do you notice that there's a lot of symmetry going on in this function? So if I know the answer to this, shouldn't I make a good prediction on what this one is, and shouldn't I be able to make a good prediction on what the y and the z are? Right, you basically just switch, each one. You get one variable. If this one has an answer by x, this will have an answer by y, this will answer a z. They all combine really nicely to give you the final answer that they have there. But time has beaten us. So I'm hoping that is enough. I'm going to go in as soon as I can, as soon as we leave here, in fact, and then I have another meeting to do. And I'll